Hello and welcome to the 2023 National Institute of Justice Forensic Science Graduate Research Symposium. We have some great presentations on the agenda today, but first I'm going to hand things over to our moderator, Tracy Johnson, so she can say a few opening remarks.
Welcome everyone to the second annual Graduate Research Symposium and Poster Session. I'm joining you from Denver, Colorado, while attending the International Symposium of Human Identification during Forensic Science Week. So over the next 2.5 hours, we have 7 oral presentations representing a broad spectrum of forensic disciplines presented by up-and-coming forensic experts. We also have over 30 posters for participants to browse at your leisure following today's presentation. But for today's first presentation, we have HyeokJae Lee from Iowa State University presenting on fracture mechanic basis for comparison scales of fracture matching. So let's hear it, HyeokJae.
Good afternoon. My name is HyeokJae Lee, and I'm a graduate student at the Aerospace Engineering Department, Iowa State University. Today, I'm going to talk about fracture mechanics basis for the comparison scales of fracture matching. Since portions of this research have been funded by the NIJ, please note that opinions and point of view are representative of the individual presenters and not the US DOJ. I'm going to talk about motivation and objectives, and then the details of this study with some conclusion. The National Academy of Science reports call for establishing the scientific basis and reliability of many forensic methods, and fracture matching is one of them. Forensic scientists match the fracture edges as a 2D puzzle pieces or do fracture surface comparison. In fracture mechanics, we have a description of a process shown ahead of the crack tip, varies by material and loading history, wherein the driving forces for fracture exceed the intrinsic material resistance to fracture. We can really use this concept to provide a quantitative analysis of the fracture matching process. To run ongoing work of forensic scientists, we found that forensic fracture patches covers many classes of materials found in a crime scene. Here, we focus on metal fragments that undergo brittle fracture with limited deformation, so we can have near locally planar fracture surface that could be easily imaged with 3D topographical microscope. A key finding is that the association of fragments is subjective and the confidence in the decision is not identified. So, experience does not substitute for demonstration of accuracy. We want to support the expert judgment by providing a mathematical and statistical basis for the examiner decision using the topographical details of the fracture surface. The topology of the fracture surface possesses unique attributes which we can quantify. The fracture surface topology depends on grain size, loading direction, environment, and how the material fracture. At what scale we should view the crack to show the individuality of the event? At the nanoscale, a crack is a bunch of separated atoms emitting dislocation at 10 nanometer. Dislocation clusters at 100 nanometer into slip bands at 1 micrometer, forming voids within the grains at 10 micrometer and progressing to the structure scale. The question is, which scale, which view the crack surface at? In our fracture mechanics toolbox, we have few things that we know. First, applied load will set a process shown ahead of the crack tip. Second, material resistance to fracture will set the mechanism which is ductile versus brittle. Third, surfaces in the microstructure will provide the weakest link for the crack to propagate. Finally, process will be affected by environment like temperature or corrosion. In fracture mechanics, we have a parameter called fracture toughness, which is the intrinsic material resistance to fracture. Over a characteristic scale, and not the driving forces to fracture, reaches such a critical limit and the local crack propagate. This strength scale, the fracture process zone is about 2 grain in diameter for brittle materials. Accordingly, fracture mechanisms are prevailed over a limited range of the physical scale and thereby can be identified only at a given magnifications. Here is crack propagation under tension, viewed with different magnifications. So, which scale should we consider to analyze? We asked our forensic science collaborator John Vanderkolk, and he said we should use low magnification of A and B. At high magnification C to G, the details of the fracture mechanisms are prevailed and the topology may not be distinguishable. So actually there is a basis for the choice of the scale. Mandelbrot et al. 1984 first showed the self-affine scaling properties of fracture surfaces to quantitatively correlate the material resistance to fracture with the resulting surface roughness. So, I am here to show a topography image acquired by 3D microscopy, and to the right, I am showing a statistical measure called height-to-height correlation. It's scaled with the analysis window delta x, indicating self-affine. Then it deviates and saturates at larger analysis window, which shows the uniqueness of the surface texture. For the example shown here, delta H saturation is at about 50 to 60 micrometer. From fracture mechanics, L0 equals 2 dg and dg is 25 to 35 micrometer for the examined material. Accordingly, L0 equals 50 to 70 micrometer or F equals 50 to 20. So, a field of view for imaging should be about 8 to 10 L0, which is about 400 to 500 micrometer. Also, we should at least reserve L0, which would require about 10 pixels. So, the imaging resolution should be better than 5 micrometer per pixel. Great, so we now have a proper way to identify the proper magnification for comparison. We generated different sets of samples and performed 3D topography imaging. We used spectral analysis on the frequency space to compare a pair of surfaces. In one set, we have a standard bending test to fracture set of stainless steel beam in a controlled repeated way. On another set of stainless steel knives, we fracture them at random. By clamping to a vise and bend, twist, or bend and twist them, you can observe the subtle differences on the SEM images, wherein bending shows straight river marks, twist shows circular marks, while bend and twist is a combination of both. For each pair of fracture surfaces, we aligned them under the confocal microscope and take a set of topographical images. For every pair of samples, we take a set of 6 to 9 overlapping images with overlapping ratio of 50 to 75%. We take multiple images to improve the signal-to-noise ratio. The rationale of these values will be discussed in the next talk. Then, we perform 2D FFT mathematical operation on every image to get its spectral contents. We do our analysis in 3 steps, including image analysis, model training, and object classifications. Image analysis step, we align the pair of fragments for comparison. We acquire the set of the 3D topography images, apply the mathematical Hahn filter to accommodate for edge effect. Perform FFT to get the frequency spectral representation, then divide the spectra into radial bands and perform correlation between 2 bands within the non-affine length scale identified by the height-to-height correlation. Forensic scientists measure distance between features on the surface to provide description of the similarity. All these features and their spacing are captured over the entire surface with the FFT spectra. To demonstrate this, let us take a single line within the topography image. I am showing the topology by the red line. Its 1D FFT is shown in the top left. You will notice that there are groups of data. Each range of frequency corresponds to a physical phenomena. At low frequency that we will use for our comparison, it has the information of macro crack behavior and liver marks. Next group is the grain size distribution. And at the high frequency range, it represents the micro fracture process, void and dimpling. So for a pair of images, we calculate their corresponding pairs of frequency spectra. Define angular bands in the transition range of the non-affine deformation, and then perform correlation between these spectral bands to form the analysis dataset. Now, you can see clear separation between the 5 to 10 and 10 to 20 frequency bands. But at higher frequency, the distinction is not clear and the match and non-match overlaps. A clear separation between the match and non-match can be clearly identified. Summary results showing perfect classifications. This slide shows first and second set of bending fracture knife set. Twist fracture knife set also shows the perfect classifications. Tensile and bending fracture of stainless steel set also show the perfect classification. We also analyzed a set of hexo blade. Successful applications of the discrimination framework, box plot of posterior probabilities of matches for all our cases using 2 different model training mechanisms. Higher values indicate that a match is more probable. We observed that all the samples were perfectly classified to match and non-matching surfaces at a p equals 0.5 regardless of the training mechanism that we used. It plots with posterior logos probabilities of match across all combination of fracture surface pairs with classification model training by cross-validation. We observed that both types of training techniques result in similar posterior logos. The framework is general and can be applied to a diverse class of materials with very different microstructure. In conclusion, I presented promising forensic comparison framework for fracture surface comparison which can support expert judgment, provide mathematical and statistical defendable decision, and proper sample size. In future, imaging skills application to different classes, environmental degradation can be addressed. We are currently also working on ceramic and porcelain, but plastic, auto parts, wood, tapes, also other plausible applications. Thank you for listening to my presentation, and I am open the floor for questions.
Hello, everybody. We have a few questions. HyeokJae, are you ready for those?
Oh, yeah, yes, please.
Okay. All right, we'll start with the first one. So how are fracture mechanic analysts able to identify stochastic defects that contribute to the fracture pattern of the fine metal fragment of interest?
Okay. So your question is that you're also forensic scientist doing statistics, and you ask me about the difference, or?
So how are they able to the stochastic differences that contribute to that fracture pattern?
Oh, in a statistical way?
Yeah.
Actually, that about the statistic part, the next presenter, Josh, will demonstrate more details, and he will talk about mainly about the statistical part. So my presentation actually only focused on the size selection, scaling selection, and the procedure that we prepare the specimen. So to be honest, I cannot tell details about the statistical part. Yes.
We'll hold that question for Josh.
Yes. He will present it.
All right.
Yes.
Okay. So next question: does the ideal magnification or fracture pattern zone vary depending upon the material being analyzed?
Yes. Right.
It does. Okay. And then another question. So the twisted knife fractures appear to be curved instead of linear, to some extent, with distortions of the blade shape. So does this larger scale deformation typically help or hinder fracture matching?
Whether it has any distortion or not, we always rotate and we imaging the flat surface. So actually bending or whatever it doesn't matter. But if it has many like high scale, various scale of height, obviously it is we need some tools like height to height adjustment, or like tilt adjustment, and some noise cancelling. We also use that. We do like spike noise remover, which removes the spike values. Yeah. So we treat that in that way.
Okay. Thank you for that. We have another question.
Okay.
So what analytical imaging methods would a forensic examiner need to use to apply this approach? Can you talk about those, confocal or other kinds of microscopy? What is the recommendation?
Recommendation
for any kind of imaging or analytical methods?
Based on my experience, yes, like confocal microscope, or actually any microscope can be works, I think. But the main thing is that we not only use just one imaging area, we image in consecutive images to increase the statistical reliability, like with 50% overlap, like 6 consecutive image. So I think that is important. And the magnification also is very important to ensure that they capture the fracture features. So my yes. Okay.
Okay, great. Well, I appreciate you joining us from Iowa. I'm assuming that's where you're
yes.
joining us from. So I appreciate you joining us, and we're going to move on to our next presentation. All right. Thank you. So our next presentation is from Josh Berlinski from Iowa State University.
Yes.
Presenting on gauge reproducibility and repeatability for comparative physical match.
Hi, I'm Josh. Today I'll talk to you a little bit about gauge repeatability and reproducibility for some matching fractured surfaces. I'm from Iowa State University, Department of Statistics. You can read some of my collaborators from Iowa State as well. Before getting into the gauge model, we can just set up the problem and what kind of data we have. So in particular, the process of fracture matching, we have two pieces. We'll call it a base and a tip. We want to determine if they came from the original single, now broken piece. And one way to do that is to compare large features in each of the samples. So like these two large features that are present on both the base and the tip, to determine if those were broken from the same source. Or alternatively, what we're interested in is looking at microscope pictures of each of the surfaces of the corresponding pieces and using those microscopic features to determine whether or not they are matching surfaces. And we want to know if there's some way we can automate that process. So we can use common image processing methods to convert the microscoped images of surfaces height to features that are easy to compare among different surfaces. And in particular, we take our surface height image data that we get from the microscope, apply a Hahn filter and a fast Fourier transform to get some frequency representation. And then using this frequency representation, we just take two small subsets, two bands that correspond to features of different heights that we're interested in on the surface. So using these two subsetted frequency bands, we can compare two images, one from the base and one from the tip, and simply take the correlation across each of the individual bands and ask ourselves, are these correlations high enough to consider these two surfaces to be a matching pair? Now, in order to do that, we don't just consider one microscope image for each pair of surfaces. We consider 6 overlapping images, giving us a total of 12 correlations for each matching pair. So for example here, we have one tip surface and one base surface, 6 pairs of images corresponding to 12 total correlations, 2 for each pair. Now on the right, you can see we can do this over and over again for matching surfaces and similarly non-matching surfaces to get a distribution of correlations that will inform us of the differences that exist among matching and non-matching pairs. It's important to note that while this is plotted on a two-dimensional axis, each data point is really only 1/6 of a complete observation that we have available to us. So for example, I've connected this point that we see right here, which is made up of the 6 individual data points that exist on the graph. And we transform these correlations using a Fisher-Z transformation, which essentially makes these distributions more elliptic, allowing us to use things like the normal distribution and investigate, using that, investigate the variance that exists among, in particular, this distribution for matching pairs. And we want to know which sources of variation are contributing how much to the overall spread of this distribution. In order to take these measurements that we're interested in, we have to construct some number of matching pair samples that we can work with. So in our case, we have 20 steel rods, 10 of which were broken using tensile forces, so pulled apart sort of like this left picture, and 10 of them were broken by just bending them, which is shown in this middle picture. And that gives us 2 different sets of samples that we can compare with separately. And each of the surfaces for these 2 different data sets may contain different types of features just due to the way that they were bent. So we're going to investigate the sources of variability from some kind of measurement system that we use separately for tension samples and bending samples. In order to induce variation that has sources we can isolate and study, we measure each of the matching pairs multiple times each using different microscope operators and each of those microscope operators will image the samples multiple times each. Overall, to give us a large number of these correlation matrices corresponding to matching pairs to study. And among that set of matrices for these matching pairs, there's going to be some variation. And the variation is going to be due to a variety of different sources that we've controlled for when collecting the data. One part that we can't do anything about is the variation that exists from sample to sample. So in the case up here, correlation matrices that correspond to one sample may be different from correlation matrices from another sample just due to physical features that exist on these actual surfaces of the matching pairs, and there's nothing that we can do about those. However, there is some variability in this data set that we have some control over due to the process of actually measuring the samples. And the two main ways we break that up is the variation that exists between the microscope operators and within the microscope operators. So between operator variability essentially means that two microscope operators imaging the same sample are going to give us different results. We want to know how different are those results on average. And similarly, within operator, if one microscope operator images the same sample twice, we are also going to get slightly different results. And we want to know how different are those results going to be from image repetition to image repetition. Now, in order to isolate these sources of variation, what's typically done when there are univariate measurements are what's called a gauge repeatability and reproducibility study, sometimes called gauge R&R. And what this is a random effects model that essentially tells us that our observed measurements, the yi's, are equal to some fixed mean, so the true measurements of that part, in our case the true correlation between the matching pairs. And when we observe the measurement, there is some difference from the fixed mean due to what part it is. Some parts may have different measurements. The operator who is measuring the parts, and some interaction between them, since some operators may be better at measuring certain parts than others. In this case, in this random effects model, we assume that all of the parts, operator, and remaining effects are all normally distributed with zero mean and their own variances. And importantly, we assume that these random effects are independent of each other, which will tell us that the variance of our measurements is just going to be equal to the sum of the variances of all of these random components. And all of these random components correspond to some source that we talked about previously. Now, since this variance is just some additive sum, we can be interested in the components that make up this sum. And in particular, in gauge R&R models, we're interested in the parts that correspond to the measurement process, which are going to be everything but this part effect, essentially. So in particular, we have the reproducibility parts of gauge R&R, which is the operator parts, anything that corresponds to the operator. And this represents the between operator effect that we talked about on the last slide. And similarly for repeatability, we just have this sigma squared E, which tells us how different on average repeated measurements of the same part are from the same operator. And what is typically done is some comparison between the repeatability part and the reproducibility part to tell us in general information about this measurement system that we're interested in. That gauge RNR model works well for univariate measurements. However, our measurements are these matrix-variate observations. So instead of using univariate normal distributions, we have to use what is called a matrix-variate normal distribution, which is defined here using a covariance matrix that describes relationships between the rows and one that describes relationships between the columns. And essentially what this is saying is that if we stack this matrix on its columns, then it will follow a multivariate normal distribution with this covariance matrix equal to the Kronecker product of the two row and column covariance matrices. Applying that to the matrix gauge RNR model is quite simple, since we can just replace the univariate effects with their matrix variate versions and impose the same restrictions. In particular, that all of these random effects are going to be mutually independent with their own now covariance matrices. Now for each of the models, we have two, one for the tension, one for the bending. We have 10 samples each. For the operators, we have 3 for the tension data and 2 for the bending. And for both sets, each operator measured each sample 5 times each. Now each of these covariance matrices is typically general in a matrix variate normal distribution. However, we impose some restrictions on one of them to make things a little bit easier. For instance, the omega matrices are still general 2x2 matrices that describe the covariance between the frequency bands. However, the phi matrices are now 6x6 AR1 correlation matrices, which corresponds to the overlapping images. Rather than comparing the two covariance matrices separately, we can use the matrix variate normal distribution facts to investigate only one covariance matrix. And in particular, since the random effects are still mutually independent, the overall variance is still going to be the sum of these covariance matrices for the specified components. Just now, they're made up of these Kronecker products for each component. And now we can construct quantities of interest for the variation in the measurement system, which are going to be this reproducibility covariance matrix and repeatability covariance matrix, which correspond to between operator variability and within operator variability, respectively. And to a lesser extent, we might also be interested in the variability that exists going between the different samples that we have available to us. Before we look at the total 12x12 covariance matrices, we can visually compare the 2x2 covariance matrices that correspond to the relationship between the frequency bands by looking at 95% density contours for a normal distribution with the appropriate covariance matrix for the component that we're interested in. So on this ellipse plot here, I have several ellipses, but the largest of which corresponds to the total variability. So the size of this sort of indicating the size, the total amount of variation that we have in total in our data set along these frequency bands. Now, if we break this into different components, for example, this blue ellipse is the between sample variability. So this is the variation from the part random effect with the variation from the interaction random effect added together. It's the largest source of variation that contributes to the total variability. Over again, it's not something that we're interested in. What we are interested in is these two, this black and green ellipse corresponding to the between operator variability and the within operator variability, or rather the reproducibility and repeatability, respectively. And in particular, we can compare just the total volume of these two ellipses, which we'll do a little bit later to get an idea as to what is actually contributing to the variation in our measurement system. And the results for the bending data are similar. However, one thing that is immediately noticeable is that the between sample variability is no longer the largest source of variation. Now it's the within operator variability. But again, what we're mainly concerned about in this plot is the relative sizes of the between operator variability and the within operator variability. So again, rather than just looking at the ordering of all of these different samples, we want some way to compare the size of the within operator variability and the between operator variability to get an idea of the total proportions these two components are making up of that measurement variability. In the univariate case, if we want to compare the contributions for each source of variability, we can simply take the ratios of each of the components to their sum to get a sort of total contribution score. However, we can't simply do that with the matrix-valued covariance matrices, so instead we have to find some other way to compare the sort of size of matrices. In one such comparison, we can use the volumes of the 95% density ellipses for the multivariate normal distributions that correspond to the appropriate covariance matrices. And that volume, that ratio of volume, simplifies to this ratio of determinants, which we can then scale by square root, or if we want to include the dimensionality of the data, we can scale it by the 12th root to get these sort of pseudo proportions that give us an idea of how large each source of variation is compared to the total measurement variation. So for the tension data, this value for repeatability is around 0.8, whereas for reproducibility, it's around 0.14. And while these two values are not true proportions, they don't add up to 1, what it's telling us roughly is that around 80% of the total variation in the measurement process is due to this repeatability part, meaning the differences in measurements that exist of the same sample made by the same operator at a different time. And since the reproducibility aspect is so low, it's telling us that measurements of the same sample made by different operators on average will tend to be quite similar to one another. And that, to us, is a good thing, that this reproducibility aspect is so low. It's telling us that if somebody else from maybe some different lab images a sample in the same way that we've imaged ours with the 6 overlapping images and everything like that, they should expect similar results in terms of this classification problem that we posed before. And the same sort of thing is true for the bending data. The only difference is this reproducibility bit actually takes up quite a bit more of that measurement process variation. One explanation for the difference in results between the tension and bending data is due to the physical differences that exist in the sample. So for example, I have just one bending sample listed here below. We can notice that on the base and on the tip, there are two sort of large cliff-like features that are present in many of the bending images that we could look at. However, this cliff is not always present in both the base and the tip. For example, the base could be shifted over slightly to not include this cliff. And the result is that there is going to be a low correlation between the two pairs of images, since this large cliff-like feature is going to sort of dominate the frequency bands that we are looking at. However, overall, the total variation in the data sets due to the measurement system is quite low, and these problems that I'm pointing out do not really cause any serious issue when it comes to the classification problem that we talked about earlier. Thanks for listening. So now I'll let it go to any questions.
All right. I think we're ready for some questions here, Josh. All right. So I'm going to start with one from the audience. And so we're calling this variability graphs. Why do you think that within operator is larger than between operator variability? Or would you expect it to be the other way around?
Yeah, that's a good question. And generally in typical gauge R&R studies or other analysis of variance, it is the other way around. But in our investigations, we haven't been able to think of any specific confounding factors that we could include. But one idea that we had is that the operators are, for the most part, imaging sort of the same exact area on these surfaces at a microscopic level. And sometimes the operators, they don't follow their own guidelines to the T. So if some of them are following it exactly and some of them are not following it exactly, that might throw off estimation a little bit.
Okay, understood. Can you tell us what are the next steps for your research?
Yeah, so as HyeokJae talked about previously, we're working now on ceramic and porcelain materials, particularly is what we're working on now. We'll eventually move on to things like plastics, I'm sure. And one other thing that we're working on recently is sort of looking at the pre-processing steps that we're doing, that Han filter step, to try to eliminate the effects that I talked about at the end with the edge effects for the bending samples.
Mm-hmm. Can you tell us, how does that image processing used for automated fracture matching work? So what are the aspects that are being visualized and compared between the operator and the within operator difference to create this determination?
Yeah, I can only talk a little bit about that, since most of my aerospace co-authors have gone through the pre-processing steps. But essentially the two steps are the Han filter and the Fourier transform, like I talked about. In the Han filter, we use to eliminate some of those boundary effects that we see, such as the bending samples. We found that not including that step gives a lot of issues. Sometimes the fractured surfaces have many problems on the edges of the surfaces. And the Fourier transform is, as far as I'm aware, sort of in an abstract way extracts the features that we're interested in the ones that we found through testing, looking at different areas of that Fourier transform, and gives us ideas of the location on the surfaces. And putting that all together, comparing them via correlations, is really sort of abstract. So it's hard to pull together the specific features on the surface, telling us which ones are good and which ones are bad. We're sort of just measuring the entire process that we have all together.
I have one last question for you, Josh. So it seems to me that the work that you're doing has massively sort of transformed the way that fracture match comparisons are being performed within forensic science. So in the eyeball check, sort of a quantitative or qualitative assessment, this very precise quantitative assessment in terms of like that fracture match comparison. How do you see presenting that kind of information within a court system, moving from sort of the qualitative to the quantitative?
Yeah, so that's something we still have to, we put in a lot of thought about, and we talk about this often. I think it boils down to a lot of sort of thinking about our process scientifically. What is the actual process that we're doing, capturing? And in the end, somebody's going to have to make a decision whether or not it's right or wrong. And we're hoping that this process of automated matching, if it turns out that this automated process gives a very high probability of match, maybe that can assist to the people who are doing it by the experts that we already have.
All right. Well, I appreciate you taking some time to answer our questions, and we're going to move on to our next presentation. So up next, we have Alexandra Adeoye from the West Virginia University, and she's going to be presenting on expert algorithms for substance identification applied to Cathinones.
Thank you for the introduction. Today, I will be sharing with you our continued efforts in the Jackson Group at WVU at applying our expert algorithm for substance identification to spectrally similar synthetic cathinones. Before I start my presentation in earnest, I want to make this disclaimer thanking the NIJ for supporting this research and stating that the opinions, conclusions, and recommendations presented here are mine and my co-authors and do not necessarily reflect those of the Department of Justice. Many of us are aware of the rapid emergence of novel psychoactive substances, or NPS, in the last decade and how that has increased the workload of our forensic practitioners. These NPS include synthetic cathinones, commonly known as bad cells, such as N-ethylpentylone, which is in red on our screens. One of the main challenges with emerging cathinones is how similar their mass spectra can be. So on our screens are two synthetic cathinones, N-ethylpentylone in red and dipentylone in blue. These compounds are constitutional isomers, and from their structures on the screen, we can see that the only difference between these compounds is the connectivity of the carbon atoms on the amine nitrogen as highlighted by the circles. And when we observe the distribution of the mass to charge ratios in their mass spectra, which is the primary instrumental output available to see drug analysts, we quickly see with our plain eyes how similar these spectra are, but also how difficult it would be to differentiate between these two compounds. Now, the current or consensus approach to identify compounds can differentiate between these particular compounds up to 91% of the time. However, with EASI, we have perfect accuracy in differentiating between these two compounds. So how does EASI work? Well, before that, I would like to provide some context with the current consensus approach. So this is a scatter plot showing replicate data of M over Z 149 of N-isopropylbutylone, which is another synthetic cathinone that was collected on our in-house GCMS instrument. So each of the blue dots represents the abundance of M over Z 149 from an NIB spectrum. In the consensus approach, the ideal relative abundance of M over Z 149 would be 8.23 because that is the mean or average of the data set. However, we can see that there are some abundances as high as 15 counts and as low as 5 counts. And so according to the consensus approach, neither of these replicates will be identified as NIB, even though we know that they are NIB. So this also shows that the consensus approach is not accounting for the variance that can exist within replicate spectra by just focusing on the mean. Now, this is a bivariate plot showing the same M over Z 149, but this time plotted against M over Z 206 of NIB. So these ions are two fairly abundant ions in the mass spectrum of NIB. And from this simple XY regression, we can see that there is a relationship between these two ions based on the R squared. Now, with the consensus approach, we only had one variable, which was the mean of the data set, and that could not explain the variance that we saw in M over Z 149. But by adding one more variable, in this case M over Z 206, we can explain up to 76% of the variance seen in M over Z 149, thereby giving us more predictive power compared to the consensus. Now, with the bivariate approach, we could explain up to 76% of the variance seen in M over Z 149. But what happens if we use a multivariate approach? When we include 7 other M over Z abundances from NIB into a regression model, we can explain up to 98% of the variance seen. This is an additional 20% of the variance explained, and this is a reflection of the correlated relationships that exist between these ions. Now, this means that we can accurately predict the relative abundances of these compounds using the correlations and anti-correlations found in replicate mass spectra data. And that's what we do with EASI. We take advantage of the correlated relationships between ions found in replicate EI mass spectra using general linear modeling to accurately predict ion abundances and hence better distinguishing between spectrally similar compounds. Now, another way to see how these ions behave towards one another is to take a direct look at the relative abundances of the M over Z values and how they change when normalized to the base peak. So on the plot of our screen is a mass spectra of NIB and across its chromatographic peak as a function of the retention time. And the different colors or bars that we see at each M/Z value represent one NIB mass spectrum or scan at that point in time. And each scan is produced within seconds of each other. So as we see, even though all of these scans are from the same compound, the same injection into the GC, these scans have varying abundances at each M/Z value. Now, the base peak or the most abundant peak for this compound is M/Z 100. Now, when we normalize all the abundances to the base peak, we see that the variance within the replicate scans are taken care of, but we also see some patterns emerge. We see that some of the relative abundances have changed in relation to the base peak. Some of these ion abundances, like M/Z 50, have decreased or anti-correlated to the base peak, as indicated by the red arrow. And other abundances, like M/Z 150, have increased or positively correlated relative to the base peak, as indicated by the yellow arrow. And some of the ion abundances, like M/Z 120, have stayed leveled, as indicated by the green bar. These patterns show that even after normalization to the base peak, there is still unexplained variance and correlations that the consensus approach does not account for. And so further study into the correlations found in replicate mass spectra can provide insight into fragmentation behaviors and, more importantly, help us to accurately predict the relative abundances of these compounds. Now, a simple dot product calculation, such as Pearson product moment correlation, can tell us which M/Z values have strong correlations, weak correlations, and anti-correlations, which enables us to know which M/Z abundances we can use to build our EASI models. Now, we've tested EASI with other drug compounds such as cocaine and novel fentanyl-related compounds. And to further the development of EASI, we wanted to answer these research questions. Number one being, how well does EASI perform with spectrally indistinguishable synthetic cathinones? And two, when building our models, can we work with mass spectral data from different laboratories and then account for the amount of variance we may see due to factors like different GC instrumentation, source material, etc.? Now, these research questions were inspired by our collaboration with the Virginia Department of Forensic Science through Stephen Hawkinson. We were informed that N-ethylpentylone was a frequent bust in the past few years, but there are now new cathinones on the scene. And as I mentioned at the beginning of my talk, this raises some new challenges to the current standard practice for seizure analysis, as practitioners are required to test all suspected unknown compounds with reference materials on the same instruments to properly validate their findings. While these are sound practices, the challenge here is acquiring the increasing number of standards for the increasing number of emerging drugs. And these standards are typically expensive, thereby increasing the cost to crime labs. Not only that, as we saw earlier, these emerging compounds have become more structurally and spectrally alike every day. So that increases the difficulty in resolving their spectra. So we now have to be innovative in our problem solving. Can we make drug identification without the use of contemporaneous standards and analyses? So to tackle that question, we amassed a spectral database of over 3,000 cathinone spectra for EASI analysis. Our mass spectral database comes from two labs, our research lab at WU and the VDFS crime lab system. We then collected all our data on 4 different Agilent GCMS instruments. And the spectra was collected over a 2-month period to incorporate day-to-day variance. Now, these are some of the compounds collected, and as you can see, they have similar structures, and most of them are constitutional isomers. So to develop our EASI models, our collected replicate GCMS data were filtered into training and test sets. We then built our model using the 20 most abundant ions and tested the regression models for normality before then applying the training set models to other spectra. And finally, we assessed the accuracy of the EASI models using these 4 evaluation metrics. But for this presentation, I'll be showing the results for just the mean absolute residual. The average or mean absolute residual is a metric that shows us how the predicted spectra differ from the measured spectra. So this is the average of all the residuals between our measured or observed spectra and our EASI predicted spectra. So on the screen, we have population plots with our known positives, or KP, which is our drug of interest, in yellow. And this is compared to all other cathinones in our database, which are the known negatives, or the KN, in blue. And then the y-axis is the range of the mean absolute residuals. The left plot is for the consensus approach, and the right plot is for EASI. And in this case, our drug of interest is N-isobutylone, or NIB. In this slide, we cannot easily see if there is any separation between the known positive distribution and the known negative distribution. But if we zoom in on the y-axis, then we get a clearer picture. In the consensus plot, we can see that there is no clear threshold where we can make errors identification. Any threshold we choose will be added to minimize the false positives or the false negative identifications. However, with the EASI plot, as indicated by the green box, we have a range of thresholds where we can make errors identification. Hence, we see EASI outperforming the consensus approach. Here is another population plot, but we have a different drug of interest, N-ethylpentylone. As we can see, with the consensus approach, we are still struggling to make errorless identifications, whereas with EASI, we can confidently distinguish between N-ethylpentylone and other structurally similar cathinones. So in addition to the evaluation metrics, we plotted a receiver operating characteristic curve using both the consensus approach and EASI to determine the diagnostic ability of each measure as a binary classifier. So the closer the curve is to the upper left corner, the larger the area under the curve, and the better the metric is used as a binary classifier. Okay, so in a raw curve, we have competing distributions of known positives and known negatives. And so the greater the separation of these distributions, the better the area under the curve, which means we have an easier time deciding what threshold to use. So we generated raw curves using the mean absolute residual for the consensus approach, which is the red line, and EASI, which is the blue line. From the area under the curve, or the AUC, we can see that the AUCs are high for both models, but the EASI model outperforms the consensus approach with a perfect AUC, showing the superior capability to be used as a binary classifier. Now, as stated earlier, we collected replicate NIB data from our in-house GCMS and in the VDFS Prime Lab systems. We determined that EASI can account for the variance seen in replicate data between labs, even though the mean abundances are different. So as we can see in this plot, the data from Lab 2 in blue follows the same regression line as the training set data from Lab 1 in yellow. This plot also shows that EASI can predict data that falls outside the training set. In other words, we can extrapolate outside the training set, thus making interlaboratory comparisons and drug identifications without in-time reference standards possible. So in summary, EASI is a robust algorithm capable of distinguishing between compounds with similar spectra, and as we saw earlier, applied to cathinones and in our previous work done with cocaine and fentanyl analogs, we have seen consistent results, hence making EASI reliable and reproducible. We've also seen how EASI can handle different sources of variance, and so with EASI, we can compare spectra between laboratories, hence reducing the need for reference spectra. This means that if we can create a large enough database with reference spectra that can be accessible to crime labs, with EASI as the algorithm tool, we can make comparisons without the need for contemporaneous analysis. I'd like to acknowledge that this work is funded by the NIJ. I also want to thank the following people for their contributions in the development of this algorithm, as well as the Jackson Research Group at the VU for their continuous support and encouragement. Thank you all for listening. The QR code leads to our publication on EASI, and I'll be happy to answer any questions you may have.
All right. So we have a few questions for you today, Alexandra. So I'm going to start with the first one. So is the goal of EASI algorithm, by the way, I love the name, that's great. Is that algorithm to replace currently existing algorithms, or is it going to be a supplement?
Right. So our goal is actually to be a supplement. So the current algorithms, which is I believe the NIST simple similarity search or the hybrid similarity search, works very well. Our goal here with EASI was to really focus on isomers that were very structurally and spectrally similar. So if the regular algorithms can easily differentiate between those two, that's great. But we really wanted to focus on very spectrally similar isomers, and especially in cases where maybe crime labs may not have access to reference standards, so we can just use the algorithm as a way to extrapolate beyond just the data is collected in one lab and compare to standards collected anywhere else.
Okay, thank you for that. So is the algorithm now ready for like practitioner use?
Yes. So it's not exactly in one graphical user interface, kind of like the NIST MS search, but there is no barriers to using it. In our publications, we've in detail explained the mathematical equations behind it. We've given very detailed explanation on how to use the quotient coefficients, how to filter the data. So there is no hindrance in using it. And we're also happy to work with any crime labs who would want to collaborate with us on any of their crime lab data.
All right, excellent. So I heard you say that if a crime lab would like to use your algorithm, they can reach out to you for assistance.
Absolutely, absolutely.
Excellent, great to hear. So why did you choose 20 ions for this model building?
Right. So the 20 ions are a bit arbitrary, but we did want the 20 most abundant ions because we believe this will be reproducible across all instrumentation. Okay. So in a case where you might have like a poor quality spectra, we would still be able to see those most abundant ions and hence be able to use them in our algorithm.
Okay, thank you for that. And how many spectra do you need to build a model like yours?
The more the better, especially if they come from different sources to just kind of incorporate that variance in our model building. But we have done some power analysis and we saw that you can use as little as 100 spectra for a training set and you can still get pretty good results.
Okay, that's excellent. So I love that term power analysis. That's really great to hear, other folks in other disciplines applying that kind of analysis. So you mentioned the previous compounds and drug classes used. What other compounds are you planning to test next?
We are currently working on trying to differentiate between THC and CBD. We know those are two compounds that are very difficult to distinguish between. Other than that, we also want to focus more on tandem mass spectra. So all of the work we've published and presented on is on EMS spectra, so GCMS. And we're aware that there are crime labs who have tandem MS capabilities, and we know that those databases are building, so we want to make sure that our work can also apply to those areas as well.
I'm glad you mentioned the difference there between CBD and THC, because that is, a important assessment that laboratories are having to make now. That, but also having to quantify the THC component as well. So thank you for that. Appreciate it. How does EASI account for retention time? Is this the intended for use when you have co-eluting or overlapping peaks, or can it be used across the analytical runtime?
So EASI is targeted at the mass spectra or mass spectrum of the compounds. So it's kind of an independent analysis of the retention time. But of course, most crime labs do use the retention time in combination with the mass spectra to identify or characterize compounds. But EASI, our algorithm is just targeted towards the mass spectra in the event that for some reason we do not have access to the chromatogram. In cases of co-eluting compounds, well, there is already a software called AMDIS that helps to deconvolute collecting spectra. So even after then, we can still apply EASI to the mass spectra there, but that's kind of the focus of our algorithm.
Okay, thank you. I appreciate that. One last question. So is the threshold between known positives and known negatives under EASI unique to the compound of interest, or can it be used across drug classes?
Those thresholds are unique. So if we had any kind of drawback, that would be it, where we would have to build a model for each drug we come across to determine what those thresholds are and how confident we can be when we do find those thresholds.
Okay. Well, thank you, Alexandra. I really appreciate the work that you've done presenting some of the work around NPS, which is a very important, facet of the disease drug discipline. So Appreciate that. And we'll be moving on to our next presenter. So our next presenter is Kate Vannoy with Purdue University, and she is going to be presenting Everlasting Bubble Wall for electroanalysis of aerosolized illicit substances. All right, let's hear from Kate.
Hi everybody, my name is Kate Vannoy. I'm starting my 5th year at Purdue University under the research advisement of Jeffrey Dick. Today I'm going to be sharing some of our progress on developing in-field sensors for illicit substance detection. More specifically in this talk, we're going to cover electrochemical methods for the detection of liquid and solid aerosols, and in this case those aerosols will be comprised of methamphetamine and fentanyl. First, I would like to address why we are choosing electrochemistry as our detection strategy. The instrumentation required to run electrochemical techniques is small and affordable. This is a picture of my co-author, Lynn Krasinski. Here we're helping electrochemistry students to build their own potentiostat. You can see the circuit board that she's using. It's very small, and that's the size of the entire instrument. And then any of these potentiostats that were operational after this workshop, we donated to local high schools. We weren't particularly sad to see them go because they cost us only about $50 to make. And then in addition, electrochemistry provides real-time detection and can also give us a binary readout if we're looking at whether or not there is or is not a peak in voltammetry. So voltammetry is pretty simple. It's basically just measuring how current responds to a changing potential. And the peak current in that case can inform us on the formal potential of the analyte. That gives us a little bit of specificity. So for example, here are 4 overlaid linear sweep voltammograms for cocaine, meth, heroin, and fentanyl. This y-axis is current, but you can think of it as rate or intensity. And then the x-axis is your potential, and in this case we're just sweeping the potential starting here and going in the more positive direction. And then you can also see that each of these illicit drugs is readily oxidizable on a carbon electrode when they're dissolved in some salt water. This brings us to an interesting limitation of electrochemistry, namely that almost all electrochemical measurements rely on 2 electrodes completing a circuit through a conductive solution. So here's a pretty typical benchtop electrochemical cell. In this case, the middle electrode here is the reference electrode, which is added to have a lot of precision on this potential readout, or this x-axis that we talked about. But to make a very simple measurement, you really only need 2 electrodes, the working electrode and the counter electrode. So why am I framing the solvent requirement as a limitation? Well, we want to analyze aerosols. And so now we basically know that we're going to need to capture the aerosols in a larger test volume. At this point, I haven't really told you why we're so interested in aerosols. Most of us at this conference are probably pretty familiar with the dangers of fentanyl. Fentanyls are an extremely potent opioid that can cause a fatal overdose after the ingestion of about 2 milligrams. And so here's a picture of 2 milligrams of fentanyl, and it's a very small amount. And so there's the potential for accidental aerosolization of this amount, and then dangerous dosages could be ingested by a first responder or just anyone who comes into contact with this powder. We're also going to be talking about liquid aerosols, which could exist around pipe users, and so vapor detection could be a very useful passive collection sensor. Pills, or a particle into liquid sampling, is a very common method to collect aerosols for analysis. In this case, we want our collection system to be really efficient at catching aerosols, but really bad at diluting them. So for example, if you take a droplet that's about 100 microliters in radius, in volume, and we just stretch it out into a pancake, you can increase the surface area to volume by about 2 orders of magnitude. The idea for this electrochemical cell was actually born when my advisor skipped into work one morning and asked if I could do voltammetry in a bubble wall. And by the next day we had, and so this is just a really pretty use for it. Alright, so here's a schematic of a bubble wall. Basically, I dip a bubble wand into soapy water. In this case, the soap was Triton X, that's the surfactant we used, and I also add a little bit of KCl to help with the conductivity of the solution. And then I just shoved 2 wires through the wall. The microwire, which was the working electrode, is here. That was a carbon fiber. And then the reference/counter is the second electrode, or the counter electrode, and that was made from a platinum wire. Our electrochemical measurement is happening at the working electrode, so this is just a zoom in of that environment. You can see it's this little meniscus because there's wetting involved. And so one of the biggest influences on measured current is the electrode size, which in this case is going to be controlled by how much the solution wets up the microwire. So to determine the electrode size, we electrode deposited platinum nanoparticles, and then we used scanning electron microscopy to look for the areas where there are nanoparticles versus the areas where there are no nanoparticles. And then we were able to back out the size of the effective electrode area, and that was about 150 microns. But we also wanted to know the thickness of the bubble wall generally, not just as it spreads along the microwire, but over in this region as well. And so most of us have probably been introduced to Beer's law at some point in our undergraduate chemistry. Beer's law is just relating the absorbance to the concentration of the molecule, but also to the path length of the container. So almost always we use a cuvette with a known path length, and usually that's about 1 centimeter, and we're just looking to relate absorbance with concentration. But here, if we know the concentration of our analyte, we can actually back out the path length. And so we put the bubble wand in between the laser source and the detector, and we put in a known concentration of an absorbing analyte, and we were able to back out the thickness of the bubble wall. We determined it to be about 18 microns thick. And so again, we are able to stretch a pretty small volume over a rather large surface area, which is going to hit the sweet spot for high collection and low dilution. All right, I told you that we could do voltammetry in this electrochemical cell, and here's the proof. So here we loaded the bubble solution with 1 millimolar ferrocene methanol, which is just a well-behaved electron mediator, and we get this nice classic cyclic voltammogram. This is actually 3 overlaid cyclic voltammograms from 3 different measurements in 3 different bubbles, so it's pretty reproducible. I also told you that our electrode size was going to be determined by the wetting, and so here I swap out the carbon microwire, which is a relatively hydrophobic material, with a platinum microwire, which is a rather hydrophilic material, and the current increases. And so that makes sense because current is going to be related to the electrode size. All right, now into the good stuff. Now let's load the bubble wall with methamphetamine. We can see starting at about 0.6 volts, we start to oxidize methamphetamine, and this black trace is just the background, just an empty bubble wall. From this, we know the potential range where meth will oxidize, and so we can start with a clean bubble wall, and then we can expose that to that electrochemical cell to the vapor containing methamphetamine. It's a little bit hard to see in this zoomed out view, but if we zoom in to the potential region where meth will oxidize, we see a very clear peak current, indicating that we have captured and detected methamphetamine from the vapor. All right, well, not to burst my own bubble, but my goal is to make a field deployable sensor, and we're probably all aware that bubbles pop, because these are very thin films of water, and they're evaporating very readily. Also, as we move to more hydrophobic analytes like fentanyl, the water solubility is pretty limited. But fortunately, I have written the solution, and that's moving towards an ionic liquid. Ionic liquids are basically liquid salts, which meet our conductivity solution requirement, but also solves our problem of evaporation, as these typically have very low vapor pressures. Also, drugs like fentanyl tend to be a little bit more soluble in these kinds of solutions than in water. All right, now I'm showing you the bubble wand version 2. It has a couple improvements. We've employed the bubble wand itself to be the second electrode. So this is just a metal wire that we molded into a circle, and that's acting as our reference/counter electrode, and then our working electrode is again the carbon microwire that is pushed through the thin film. I'm no longer calling it a bubble wall. I'm now calling it a thin film because we don't have water and surfactant. But again, we want to know the effective electrode size. This time it's a little bit simpler. We can use molecular mass transfer because it's no longer confounded by convection from evaporation, and this wetting is probably negligible here. And so to do this, we can just measure the current that we get from a well-behaved electron mediator like my ferrocene methanol, and then we can relate the current to the length of the cylindrical electrode. I showed you kind of the steps here. You just start with the mass transfer coefficient, which just describes how molecules are approaching a cylindrical interface, and then you can plug that into the general current equation, and then you can relate current to the length of your microwire. But just to be sure that we know the important parameters that make up the geometry of our suspended film, we made a finite element model of the system. And so you can actually see here, when we simulated the voltammetry of 2 millimolar ferrocene methanol, it matched pretty well with the experimental voltammetry of 2 millimolar ferrocene methanol. And so that tells us that our geometry assumptions are pretty valid, and in the future we might be able to be quantitative, relating the measured current to the concentration of important analytes. So that is pretty encouraging. All right, finally, we're going to use this for the collection and detection of solid particles. Again, as a proof of concept, we're going to start with ferrocene methanol. So here we have just dipped a glass capillary into ferrocene methanol powder just to obtain a small amount of powder at the end, which we then dipped into the suspended ionic liquid film, which is here in this support. This is just a controlled method of introducing solid particles into the electrochemical cell, and future directions are going to be aimed at aerosolizing the powder for collection. But from the voltammetry, you can see that before the solid particles were introduced, that's this black trace, there was no Faradaic current in the potential region that we would expect the ferrocene methanol couple. That's around 0.2 volts. But after the introduction of ferrocene methanol, we are able to resolve that pretty typical cyclic voltammogram here, centered around about 0.2. So our current experiments right now are applying this method towards fentanyl detection. And so one of the first shifts we made when we were going into fentanyl detection was we swapped cyclic voltammetry for differential pulse voltammetry. So cyclic voltammetry is what I've shown you throughout this whole presentation. It's just a very simple ramp of potential, and it makes this triangular waveform. Differential pulse voltammetry is the same ramp, but there are some small potential steps along the ramp, and that's just allowing us to subtract out some non-Faradaic current. Basically, it's just a background subtracted cyclic voltammetry. That's giving us a little bit of extra sensitivity. But still, all we're looking for is a current peak to act as our binary signal. In this DPV, you can see that when we have our ionic liquid suspended film and we put 10 millimolar fentanyl in it, we can observe a peak around 0.9 volts. And of course, in the background, we do not see that peak. And so while 10 millimolar fentanyl might seem like a pretty high concentration, this volume actually corresponds to the capture of about 17 micrograms of fentanyl. And then, so right now we're pursuing the detection of actually aerosolized fentanyl powder, but obviously this needs to be done with a lot of care, and so we're still very carefully working on that. Great, and so with that, I just want to acknowledge my co-author, Lynn Krasinski, who's back here, for all of her contributions to this work, and then of course my research advisor, Jeffrey Dick, and then also the National Institute of Justice for their fellowship support and the mentorship on this project from Dr. Francis Scott. I would really be happy to answer any questions or hear any suggestions, and so I provided my email address here to facilitate future correspondence. And so thank you very much for your attention, and I really look forward to hearing from you.
All right. Well, thanks, Kate, for joining us. I think we do have a few questions for you. And so we're going to start out with how would the voltammetry or electrochemistry method work with drug mixtures or additives in the aerosol?
Yeah, that's a tricky question. So electrochemistry is pretty sensitive, and it's really deployable, but probably where it suffers the most is with selectivity. And you can get a little bit of selectivity, like I was kind of mentioning with where you see things oxidized, but once you have more than one oxidizable species, it becomes very complicated. And a lot of these drugs are proton coupled, so they also shift in different pH environments, which also makes it kind of complicated to pin down a potential. And so you basically have to add an additional measurement. So we've done this in the past by maybe incorporating a way of isolating only the analyte to the electrode surface, either by like unlikely imprinted polymer, or you can put like a carbon nanostructure that likes to absorb these materials, or you can precipitate them out. But there usually has to be one more step to be very confident in a mixture that you're measuring what you think you're measuring.
Okay, understood. So that's to measure both analytes. But I guess a similar type of question would be, if in that environment there are multiple analytes, can you detect the fentanyl regardless of what, I guess, is present in the background?
Yeah, I think that if it's not oxidizable, whatever the interferent is, if that's not oxidizable, you're probably okay. So if it's like, baking soda, maybe you'd be all right. But if you get into some of, like, if it's lacing heroin or if it's lacing methamphetamine, you're going to have a little bit more difficulty.
Got it. Okay. All right. So the next question, does this method work only for compounds in aerosol samples that are oxidizable? I think you've answered that. Sounds like yes. So we'll move on to the next one. How you measure the voltammeric peaks across the compounds of interest?
I think I touched on that one briefly. Just to be sure what you asked. You asked how representative are the peaks of what compound I'm trying to measure? So I kind of cut out.
Oh, so sorry. Sure, no problem. I can ask again real quick. So how unique are the voltammeric metric peaks across the compound of interest?
Gotcha. Yeah, they are somewhat indicative of the molecule. If you know everything about your solvent, so there's a lot of things that go into it, solvent and pH are things that I've already mentioned. And then, of course, adsorption will also shift that peak. And so there's a lot of things that can shift the peak. So if you know everything you need to know about it, then it's perfectly indicative of your formal potential of your molecule. In most cases, it's just kind of like an experimental measure, and we call it a halfway potential because we're not exactly sure all these things that are contributing. And so as long as you have a standard to back it up against, which of course in the lab we do, it's not so bad. It becomes more complicated, of course, going to something field deployable where you're probably not bringing a standard out there to be sure.
Understood. Yeah, but I think in that particular case, if you're field deploying, you're doing that for maybe different reasons, either for sort of safety of the responders. Mm-hmm. Yeah, exactly. Or maybe just awareness, knowledge. And so just an indication might be enough to proceed with caution.
You can probably get a window of about 200 millivolts where if anything shows up in that window, let's take some precautions. And so I think that's totally reasonable, but pinpointing maybe a little bit more difficult.
Got it. One last question here. So will the wetting geometry remain consistent across samples as long as they use the same surfactant thin film composition? So that may be related to maybe sort of the previous model. Is that related now to your updated model?
Well, when we were doing the soap bubble with the water and the surfactant, it was amazingly reproducible. I thought the same thing. I thought, okay, every time I make it, it's going to have different wetting. But every time I made a new bubble and threaded something through, it was exactly the same peak currents, which means it's the same electrode area, which means it's the same wetting, which was incredible. For the ionic liquid, we're having a little bit more of a challenge because it doesn't evaporate. So with the water, you can push it through, and then anything that's in contact with the solution will stay, and anything that wasn't will probably be gone. That film is not going to exist. If you push something through the ionic liquid, it's not going to evaporate. And so any kind of juggling or jiggling the wire, it's going to wet the wire, and then we're seeing a little bit more differences. And so as long as you're not trying to be perfectly quantitative, it doesn't matter. But if you do want to know your electrode size, you have to be quite careful with the ionic liquid. The water, again, was very easy.
Yeah, no, I was going to say you moved from version 1 to 2 to solve the evaporation issue, and then of course you're in factors, and you have to work around those challenges.
Yeah,
but that's science, right?
Yeah, right. It's just how it goes, and it depends what you want to prioritize.
Exactly.
Do you want it to be deployable, or do you want to really, have a reproducible peak current every time? Mm-hmm. So you prioritize.
So it does sound like potentially with the work that you've done, you could potentially go both ways. Having a field deployable with the intent of just, letting the individuals know, whoever is in that vicinity or area, to proceed with caution, or there's the indication that fentanyl is present. And that could mean a lot of different things, right? That, someone is using fentanyl or has used, or it's there to be careful. But it sounds like you could potentially also move towards maybe a desktop or a laboratory model as well. So that's really exciting.
Yeah, we're doing right now. We're doing the fentanyl stuff for more of an application, but we're trying to measure single aerosols, and we're trying to do something very fundamental and like look at the liquid air, boundary by catching it on a hydrophobic ionic liquid. And so there's a ton of promise. Like, I think there's 2 papers, one is mine and one is another, that have ever made this kind of electrochemical cell. And so there's a ton of stuff to do, which has been super fun.
Yeah, no, I really hope our audience appreciates that when you're sort of developing this kind of new technology, that there's a lot of factors involved in this, and this is really promising and exciting. So I appreciate you joining us and answering questions. And with that, we're going to move on to our next presenter. So our next presenter is, my apologies. So we have Balaji Sundararaman from the University of California, Santa Cruz, and he's going to be presenting on targeted genotypes of DNA isolates from rootless hairs. So let's hear from Jay.
Hi, thank you for the nice introduction. My name is Balaji. I'm a postdoctoral fellow at UC Santa Cruz. I'm going to talk to you about targeted genotyping of DNA isolated from rootless hair for genetic genealogy. These are our ethics declarations. What is genetic genealogy? So the current forensic DNA workflow begins with a forensic specimen. It could be in a hair, it could be a bone, it could be any human remains or dried blood. These samples get processed by a forensic lab where they isolate DNA from these samples. And then they subject these for CODIS marker testing using capillary electrophoresis. When they were able to successfully generate a genotype file from these 13 or 20 STR markers, they upload this CODIS profile to CODIS database for a search. Once they find a hit, the case is solved. But 2 things can go wrong here. One, the quality of the DNA could be really bad. That then tends to leave certain CODIS marker not to be genotyped, or like the entire CODIS genotyping could fail. So in these cases, we have no or partial profile. The second case is we may generate a full CODIS profile, but then when we search on the CODIS database, we may not have a hit because that matching profile is not present in the database. In both cases, the case becomes cold and then the specimen gets stored. Due to recent developments, because of the progresses in DNA sequencing, there is a new method that led to forensic or genetic genealogy, where specimens, DNA from these cold specimens, they get reprocessed and then they were subjected to whole genome sequencing. And then they were used to generate SNP profile, single nucleotide polymorphism profiles. Once we have these SNP profiles, these gets uploaded on consumer databases, for example, like NIJ. The law enforcement can search these databases for a matching profile, and then they can construct in a genealogy map or in a familial map where they can track the relatives of the suspect. By identifying either the relatives of the suspects or the actual suspect itself, they can then ID the suspect and then the case gets solved. So the important step in this entire genetic genealogy workflow is generating the SNP profile. So the current method of generating SNP genotyping workflow begins with the foreign specimen itself. Then it gets processed in the forensic lab for DNA isolation. The DNA could vary in quality and quantity based on the specimen. And then all of these DNA is converted into a sequenceable library where we put together adapters at the end of the DNA molecules that enable them to be sequenced on the Illumina machine. Now actually it's the Verogen machine. These machines generate millions of sequencing reads, short DNA fragments that are spanning across the genome. Once we have these data, we can map it to a reference database. And then by comparing the reference to the actual data, we can identify the SNP markers. So the advantage of this current workflow is it can identify SNPs genome-wide. It can tend to output up to 1 million SNP markers across the genome. That actually enables for a deep familial search. We can go up to like 7th degree or sometimes even a 10th degree relatives. But there are limitations. One, it's really expensive because like we have to sequence the entire human genome. We tend to spend a lot of money on the sequencing site per sample. And then the second disadvantage is because sometimes the law enforcement agencies want to cut down on the cost, they tend to sequence less of the sample. So there are methods where we could sequence just like 1 or 2 times the entire genome. So it's called like 1 or 2x coverage. So it's a low coverage on the entire genome. For these kind of samples, they use a statistical method called imputation, where they try to identify the genotype based on the allele frequencies. Because of low coverage and imputed SNP genotypes, sometimes these whole genome generated SNP profiles tend to be matchy, that they match actually multiple samples or like sometimes even an entire database when used for genetic genealogy searches. And then the other limitation is because there is a statistical method, the imputation genotype created by imputation may not be accepted in the court. So to overcome these disadvantages, we came up with a method called targeted SNP genotyping, where we use targeted sequencing for genotyping the SNP markers. The workflow is very identical up to the library generation part. Once we have the library, we call these pre-enrichment or pre-capture library. We incubate them with our reagents. We call these SNAREs, circular nucleic acid enrichment reagents. These are complementary DNA molecules that actually go and bind to specific regions that have those SNP markers. They have modifications that led them to be bound on a magnetic bead so that like we can wash off all the non-specific and unwanted DNA and enrich only the DNA molecules that contain SNPs. This way, we are enriching only DNA molecules and sequencing only DNA molecules that have information. So the advantages here is we don't have to sequence lots. So the sequencing cost per sample is lower compared to the whole genome sequencing. And then because like we are sequencing very specifically to those SNP locations, we tend to have higher coverage at the target SNP loci. And because it's a higher target coverage, we don't have to use any statistical method. We can directly observe the data and directly call the genotypes based on the data. So it gives high confident, high quality genotype file. And then the entire workflow also works for poor quality samples, for example, samples that are degraded and contaminated, because it has an intrinsic signal to noise enhancing step. There are few limitations right now. The capture reagents, these snare baits to enrich SNP markers, either are expensive or like non-existent. And then the number of SNPs that we can analyze tend to be dependent on the number of probes that are available to enrich those SNPs. And then the workflow may also need a skilled person. Dr. Green and myself, in my PhD career at UC Santa Cruz, we started to design SNP panels. We begin with direct-to-consumer genetic test. So you could see there are several flavors of these genetic tests, and all of them tend to genotype about 600,000 markers in across the human genome. There is no overlap between these different vendors. I mean, some of them doing something medically relevant SNPs, and then some of them are doing ancestry. So not many SNPs overlap between the any two platforms. So we ended up using SNPs from a union from across the different platforms. And from our previous research on ancient DNA, we realized that our snare methods really works well on based on the GC content of the underlying target regions. So we designed 2 panels, each with 12,000 SNP markers, exclusively either at 40% GC or at 50% GC. And when we test these on the NA128 sample, we realized that these 2 different panels work identical to each of them when they were captured individually. But when we mix them together in our 36K panel here, they tend to, the higher GC panels regions tend to perform better than the low GC panels. So we designed another 72,000 panel based on a narrow 40 to 70% GC region, and we tested a hair sample from a volunteer. From our experience, we observed that SNPs in higher GC regions tend to have higher coverage compared to the low GC regions. And then SNPs at the low coverage, low GC regions also tend to be not generating any data, so we don't get any coverage on these. So we kind of confirmed that there is some bias going on here on the GCs. We also confirmed that when we compare the genotypes that we generate from the capture data with other methods, SNPs in the low GC regions also disagree with the genotypes. We kind of conclude that this is due to the low coverage depth in the low GC regions that leads to low concordance or a higher discordance. So to avoid these, we designed 3 individual SNP panels, each with 12,000 SNP markers, with this time with really narrow GC bins. We had 40 to 43% GC, 43 to 47, and then 47 to 51 GC content. And we sequenced hair samples from 5 volunteers, on average about like 11 million raw sequencing reads. And then we ended up gathering data for about 92% of the target SNPs, or about 34,000 SNP loci, with an average coverage of 7.8x coverage. Compared to these, we also sequenced the same hair samples in parallel on a whole genome shotgun sequencing. We generated about 300 million reads per sample that actually produced 2x coverage across the genome. We also compared the genotype profiles that we generated using Illumina GSA array. We compared different genotypes, homozygous reference, heterozygous, and homozygous alternatives. And the capture data seems to have really high concordance when we have a higher coverage across the sample. So just to summarize, advantage of our snare methods for SNP enrichment. We optimized the snares for analyzing degraded DNA. We optimize these snare method to enrich SNP markers from libraries made with 1 to 10 nanogram of input DNA. We also enrich ultra-short DNA fragments that are about 30 to 100 base pairs. We cost effectively made custom panels up to 108,000 SNP markers. But there is a room to expand these to up to 1 million SNP markers. Because it works by hybridization capture, we don't have to do any kind of target-specific PCRs that tend to do poorly for a degraded or contaminated DNA. We also showed that we can cost-effectively enrich SNPs, and then we can eliminate the need to do whole genome sequencing. We also eliminated the need to do imputation by directly calling SNPs on the high target coverage sites. For the cost comparison, the DNA isolation and the library preparation steps tend to be the same, so there is no savings or loss on there. But for SNP capture, we have to use the SNP enrichment reagent, which cost about $150 per reaction. But we ended up saving about $290 on the sequencing front. So overall, we are saving about $140 per reaction. Just to conclude the talk, we demonstrated the influence of GC content on target SNP enrichment. We optimized and designed panels with different GC contents. Our final panels contained 36,000 SNP markers, from which we used hair samples from 5 volunteers and compared them with whole genome sequencing. And SNP capture enrichment is 100 times data efficient compared to the whole genome shotgun sequencing. The cost effectiveness and adaptability of our method needs to be tested on the field samples. With that, I would like to thank my professor, Dr. Ed Green, and my team at UC Santa Cruz. I would also thank the HyeokJae NIJ funding. I was a GRF grantee from 2020, and my professor is also funded by NIJ. At this time, I want to extend my gratitude to Ms. Kathy and Dr. Greg at DOJ, who managed my project and who helped me to succeed on what I did today. With that, thank you, and I would like to take any questions. Thank you.
All right. Thank you for joining us today, Balaji. And you both you and I are here at, in Colorado at the ISHE conference. So let's start with a few questions. So why use 1 to 10 nanograms per hair library hairs produce a low concentration DNA?
Hi, Daisy. Yeah, thank you. Thanks for the question. So in our lab, we actually started this project by sequencing hairs from 50 volunteers. For this capture panel, I just used 5 volunteer hairs. So for that larger panel, our objective is to go down to as small as possible. Though for some individuals, we got more than 10 nanograms. The DNA yield and quality depends on, it varies from individual to individuals. Just to use a standard, we kind of picked the lowest number, like 1 to 10 nanogram, and we kind of kept using that for all the individuals. But the methodology can be used for any quantity of DNA, 1 nanogram and upwards.
Okay, understood. Thank you for that. All right. So next question, why do you see a small number of SNPs in the concordance between the GSA array and the capture data?
Yeah, that's a great question. So for this larger panel, what we actually also collected is we collected saliva samples from the same volunteer. With that saliva DNA, we had a matched Illumina GSA microarray data. We kind of considered the microarray as a gold standard of the SNP genotypes and wanted to compare the SNP genotypes that we generated from the SNARE's capture data. When we did that, we find only a small number of SNPs overlapping with the GSA array. And then we realized that the Illumina GSA array is designed based on medical research and with objectives to find human variation in the entire population. But when we designed our SNARES panel, we designed a really high minor allele frequency SNPs. So the overlap between those two SNP sets are very small. And that's one of the reasons we see a small number of SNPs that are concordant between the GSA array and the capture data.
Got it. Yeah, I mean, for our audience out there, a lot of these techniques, methods, we've borrowed from the medical community. So, adapting and adopting them means sort of a transition from the original intent use development, what we're using for now. All right, so the next question, how do you compare whole genome versus SNP enrichment?
Yeah, that's another great question that I've been seeing people here at EASI meeting that seems like most of the forensic community is moving towards whole genome, but everyone realized that doing whole genome is going to be more expensive because we are already dealing with a degraded DNA and a low quality of DNA. And once we convert all of the DNA that we isolate from hair or bone samples, we are converting all of the non-human unwanted DNA into a sequenceable library. So when we do shotgun whole genome sequencing, we are wasting a bunch of money on sequencing microbes and other things that we are not really interested in. So that's kind of the disadvantage of doing the whole genome sequencing. By doing the SNP enrichment, by doing a targeted sequencing approach, we are eliminating all of these possibilities, and we are just magnifying onto the SNP locations that are more informative on identifying the individual.
All right. Well, we don't have any more time, Balaji, for questions because we've got to move on to our next presenter. So I appreciate you finding a quiet space here in Denver at the EASI meeting to answer our questions, and hopefully we can connect a little bit later and talk about your poster.
Yeah. Thank you, Tracy, and thank you, Rebecca and Natalie, for bringing me in this webinar. Thank you.
All right, take care. And we're going to move on next to our next presenter, and that is Coral Smith. So Coral is with the West Virginia University, and she's going to be presenting designing a novel reagent and protocol for unified recovery of nucleic acids, proteins, and small molecules from trace and degraded samples. So let's hear from Coral.
Good afternoon, and thank you for coming and listening to my talk. I'm going to be talking about a collaboration with GE Research and West Virginia University. We're working on designing a novel reagent and protocol for a unified recovery of nucleic acids, proteins, and small molecules from trace and degraded samples. The research presented here is supported by the National Institute of Justice and the U.S. Department of Justice. The opinions, findings, and conclusions or recommendations expressed here are those of the authors and do not necessarily reflect the positions or policies of the Department of Justice. With the increasing sensitivity of DNA technology in recent years, trace and degraded samples are increasingly common in forensic laboratories. There are commercially available kits that are optimized for trace DNA extractions. However, these kits focus on recovering DNA, but disregard all of the other components of a sample that may be informative. It is well documented in relevant literature that analyzing molecules other than DNA that contain a plethora of information that could prove useful to investigators trying to piece together the events of a crime. For example, RNA is widely reported as being increasingly useful in terms of body fluid identification. Since we have the technology to generate a DNA profile from as little as 6 or 7 cells, the question has been raised about the source of the profile obtained from the sample. How can we be certain that the profile generated actually originated from the body fluid stain and was not left behind on the surface in some other manner, such as touching a surface or transferring DNA from one surface to another? Profiling of SNPs in the mRNA and matching those to the DNA of the contributor could be the answer. Although it's not used in criminal cases in the United States, other countries have adopted this technique into their laboratory practice. Additionally, proteins, specifically genetically variable peptides, can also prove useful and informative in the absence of a DNA profile. Currently, there is no kit on the market that is optimized for DNA recovery as well as RNA from challenging and trace and degraded samples. Our goal is to develop a new reagent for nucleic acid recovery for trace and degraded biological samples that's also non-destructive to all the other analytes that may be in the sample. Our method is robust enough for near complete capture of all of the available DNA and RNA in the sample, while remaining gentle enough to preserve other potential analytes of interest. With conventional workflows, an analyst would need to either divide the sample and perform multiple extractions, or make the decision to pursue the desired DNA profile while disregarding any RNA that may be present. Our method allows for simultaneous extraction and purification of both. This research seeks to demonstrate simultaneous recovery of DNA and RNA from trace and degraded biological samples, as well as successful DNA and mRNA profiling from diverse body fluids for forensic applications using case-type samples, while also retaining other potential analytes. The primary goal of this method is to complete DNA capture and elution from our beads. So the first analysis occurring is DNA profiling, followed by RNA profiling, looking for body fluid specific targets. Subsequently, our unique buffer compositions are non-destructive to other analytes, so with emerging technologies, genetically variable peptide analysis may be possible to gain additional insights into individualization of the sample. Our method offers a simple and unified workflow for DNA recovery, as well as retention of other analytes of interest in one efficient process. We begin with a brief lysis step of the forensic sample. Conventional processing methods use harsh buffers and reagents, such as guanidinium and proteinase K, that destroy everything but the DNA that they're interested in. We achieve efficient cell lysis through a unique formulation of reagents that are already commonplace in every laboratory, but are also non-destructive to the other analytes of interest. From there, we add in our binding vector magnetic beads and through a short binding process of approximately 30 minutes, we end up with all of our nucleic acids completely bound to the beads, while all other components are retained in the supernatant for potential downstream analysis. Our nucleic acids will then be eluted from the beads differentially. Our current protocol elution buffer formulation is not PCR compatible, so eluates are then purified via microcon purification. The entire process can be completed in as little as 4 hours, so this makes it a comparably efficient method to commercially available products. It's also really easily automated because this is a magnetic bead-based extraction protocol. This graph depicts our binding vector beads performance under a varying amount of input DNA, ranging from 10 nanograms down to as little as 200 picograms. The dark blue bars represent the binding efficiency of our method, demonstrating near complete capture of all available DNA in the sample. Directly next to that, we have our elution efficiency in the gold bars, with greater than 75% elution efficiency seen across all input amounts. When compared directly to a popular commercially available magnetic bead-based extraction kit, our method performs almost equally as well, even though we are still in the incipient stages of method and reagent development. Not only is this success true under ideal scenarios, but we have seen similar results with degraded samples as well. As stated previously, similarly in this graph, near complete capture is observed using varying input amounts of severely degraded DNA. Elution efficiencies greater than 60% were observed, and we're working on optimizing that protocol for elution efficiency improvement. While this method is still under development and optimization, it's performing similarly to a well-researched and validated forensic extraction kit, demonstrating a great potential for success. Moving on to spiked-in human RNA, we have also seen near complete capture and highly efficient elution of spiked-in RNA samples, as well as elution efficiencies greater than 94%. This indicates the ability of the vector to recover all available nucleic acids from samples. Additionally, we have experimented with multiple bead formulations, and we've discovered that the conjugation of the binding vector to the bead greatly affects its performance. With one formulation in particular, we have discovered a potential for differential elution of DNA and RNA from the bead by utilizing minor elution buffer adjustments. Beginning with spiking in 100 nanograms of DNA and 100 nanograms of RNA into the same sample, we continued on with our normal binding protocols. Then by adding a lower salt buffer, we have removed most of the available DNA and followed that up with a higher salt buffer concentration to remove most of the RNA. These results were obtained using picogreen and ribogreen, respectively. Although this is just a proof of concept, it's demonstrating potential for this differential elution and further experimentation down the line. We have successfully achieved multi-analyte recovery from trace amounts of semen. On the left-hand side, there's a snippet of an electropherogram amplified via globofiler. Next to that is the seminal gelin mRNA marker indicating successful recovery of RNA and potential for body fluid identification. Both of these samples have undergone our binding and elution protocols, demonstrating buffer compatibility with downstream multi-analyte recovery. Although this is just a proof of concept experiment, we are expanding this study to include multiple markers for different body fluids. In conclusion, we are in the midst of developing a robust method for nucleic acid recovery that's also non-destructive to other potential analytes of interest. This method is consistently demonstrating near complete capture of all available nucleic acids in the sample, which makes it especially beneficial for use in trace and degraded samples. We have also achieved DNA recovery from semen and blood as well as touch deposits. Additionally, we have demonstrated successful multi-analyte recovery of both DNA and RNA from semen samples through globofiler DNA profiling and mRNA profiling of a semen-specific mRNA target. Experimentation is in progress to further optimize our protocols in multiple scenarios. In terms of multi-analyte recovery, we have demonstrated recovery of both DNA and RNA from the same sample and are looking to examine additional analytes such as proteins and metabolites depending on sample type and depending on emerging technologies in the future. As stated previously, we have successfully recovered DNA from forensically relevant body fluids like blood and semen. We are working on fine-tuning that protocol to enhance binding and elution efficiencies, as well as expanding into other forensically relevant body fluids, such as saliva, urine, and menstrual blood, as well as case-type samples. Additionally, we are investigating binding and elution in the presence of inhibitors that are commonly found in case-type samples, such as heme, melanin, and even humic acid. Our reagent and protocol are in the incipient stages of development, and we are already indicating great potential for success. We are excited to see where we can take this in the future. Thank you for your time, and I will now open up the floor to any questions that you may have. Thank you.
All right. I think we're ready for questions here. Coral, thank you for joining us from Colorado at the issue meeting.
Yes. Hi.
This has been fun and interesting. All right. Mm-hmm. So when analyzing the binder vector performance elution steps for your method compared to the commercial kit, why were the error bars so large for the commercial kit, especially for the 1 nanogram DNA input?
Yeah, so that's a great question. And so obviously when you're working with smaller nanogram inputs, you're going to see more variability in samples just because you're working with such a small amount of DNA to begin with. But in terms of the large variability, I'm not sure why we were seeing that. It was a very small sample size experiment, which is why we have not, named this commercially available kit. It's not like a full concordant study. So, yeah. So those are just the results that we saw for that particular experiment, and more experimentation would be needed down the line before we would be to name that commercial elution kit.
Yeah, understood. All right, so here we have a question from the audience. Do you foresee any challenges in implementing this workflow into an everyday laboratory practice?
Yeah, so that's a great question. And so we're still kind of in the incipient stages of development, and we're still working on, buffer formulation and bead formulation and kind of fine tuning our protocol to make it the most streamlined, unified process possible, as well as the most efficient. So one specifically eliminating before widespread implementation would be the micropond purification step. Obviously, that's not ideal. People don't want an extra purification step after DNA elution. So hopefully in the future, we are wanting to elute directly in a PCR-compatible buffer. But right now, that's not the case. So right now, we do have that micropond elution step, and it's been our micropond purification step. And it has been working really well and giving us, excellent recovery. So we're not really losing any DNA during that step. But in terms of moving into implementation, that would be one of the things we're hoping to get rid of. Additionally, we're also working on performing additional studies and trying to optimize our binding and elution in the presence of common inhibitors that are found in forensically relevant samples, like heme, melanin, indigo dye, things like that.
Thank you for that. And a question from the audience. Did the quality concentration of the DNA RNA extract have any significant effect on your results?
I'm not entirely sure what they're meaning with that question. Okay. Quality concentration, like quality as in degradation index for DNA?
So it is quality concentration of the DNA RNA have any significant effect on your results. Because you're eluting both DNA and RNA, did that affect, I guess, any of the way that you assessed that extraction method? Either the quantification, the amplification. I don't recall you mentioning any effects of extracting both RNA and DNA.
Yeah, no, we've had success with recovering both DNA and RNA from a single sample together, and that has been shown through our profiling of mRNA and DNA from the same sample. And so we've done that with body fluids like semen. We have not done it with degraded semen. Maybe that's what the question is more intending. So we have not yet done RNA recovery with DNA recovery in degraded samples. We've done DNA in degraded samples, but not DNA and RNA together yet.
I see. Okay, so that particular process has not been performed for the degraded samples yet, so you don't have results.
Correct. Yeah. So we have not like artificially degraded body fluids. We've degraded just spiked in DNA down to specific sizes, but we have not artificially degraded samples and tested them yet.
Understood.
Body fluid samples.
Yeah. So here's sort of just an observation from my point of view, at least from someone that used to work in a forensic laboratory and develop workflows and other kinds of things. I think there's like, let's not sleep on the advantage of being able to elute multi-analytes from a single sample and knowing that they're all related to that one same sample. I mean, I would say in the past, if we needed to do multiple analytes from the same sample, you needed to do multiple types of extractions. And so doing that, you're consuming more sample, but there's also always the opportunity for error or other kinds of things, so that you might have an analyte over here and an analyte that actually truly come from different samples. And by being able to elute multiple analytes from that one experimental process, that one extraction step, you can be rest assured that you're getting material from that same sample. So I think this is an interesting, an important sort of thought process, knowing that you have the actual same source when you're doing all of those assays, especially if you're doing body fluid in addition to the DNA genotyping. That might be quite powerful.
Yeah, so you bring up a couple really interesting points, specifically important for trace and degraded samples where we don't have a large starting sample quantity. So we want to get the most information possible from the little bit of evidence that we have. And so by choosing to perform like the desired DNA analysis, we are also not ruling out the potential for body fluid determination via RNA profiling, or potentially, protein analysis for genetically variable peptides, with emerging technologies and that sort of thing. So.
Absolutely. Yeah. So I just wanted to kind of bring that point forward for everybody. One last question before we go. So what buffers are you proposing to use in the lysate step to break open the cells without damaging proteins? If you can share that.
Yeah, unfortunately, I can't talk too much about our little lysis cocktail that we have going on, unfortunately. But yes, our lysis protocol is currently not damaging to proteins.
Understood. All right, so then we maybe have time for one last question, which is, with the preservation of proteins in the sample, how do you anticipate these proteins being used? I think you mentioned things with the genetically variable peptides, and then the question goes on to say, what additional information do you hope to gain from proteins?
Yeah. So in terms of the protein analysis, right now we have proven the concept that our buffers are non-destructive to those proteins. So we basically, sent those off for testing. We didn't do them in our lab specifically, but to show that this GVP analysis could be done and our buffers were preserving them. So in terms of that, we have kind of set that goal aside for now. And we are working on other areas of the process and kind of streamlining and optimizing other areas of the process. And then with hopes to go back and to finalize that sort of area of it, knowing that with whatever we do, they're preserved for any future analysis that might need to happen should the DNA and RNA not pan out, for example.
All right. Well, thank you very much. I appreciate you joining us from Denver, Colorado.
Yeah.
And
thanks for having me.
Later today.
Yes, I'll be around.
All right.
All right. Thank you.
You're welcome. And last but not least, we have our final presentation. It is Labibia Kaya with Iowa State University, and she's presenting on the primary application of blood and surrogate mixtures relevant to blood stain pattern analysis. All right, let's hear from Labibia.
Hi everyone, I am Labibia Imtiaz from Mechanical Engineering Department at Iowa State University. and I'll be presenting on primary atomization of blood and surrogate mixtures relevant to BPA. And before moving on to the presentation, I would like to thank NIJ for supporting us with their grant. Now, what is BPA? Blood stain pattern analysis, or BPA for short, is a pattern-based forensic technique which can be used to infer the probable origin of blood in crime scenes, which can help us to give helpful information in solving the crime scenes. So, during a bloodletting event, the blood ejects out as a sheet and undergoes primary atomization as the sheet breaks up. Secondary atomization of the droplets are also seen to occur due to muscle gas interaction, as shown in previous studies. Blood is an interesting fluid as compared to other fluids in that it creates a fluid web-like structure when upon impact. When the sheet expands, holes start forming in the sheet and they increase in size downstream, which then breaks up the fluid. So the time scale of these hole openings has a direct impact on droplet sizes that we usually encounter in forensics. This is why we are interested in seeing the breakup mechanism of blood to understand the fluid dynamics behind it, and also to come up with a surrogate fluid that has similar properties. So to simplify the spray pattern that we see in crime scenes, and as shown in previous slides, and replicate that same breakup mechanism in labs, we look at sheet breakup in flat fan spray. Now, sheet breakup in flat fan spray has been studied earlier, but in other fluids, and are quite limited on the properties of fluids used. In those studies, they were not comparable to properties of blood, which is what we are going to do in our study. Some of the objectives are listed here. So first of all, we would like to develop repeatable experimental measurement technique that uses a small volume of fluids, since for obvious reasons we cannot use large volumes of blood in experiments. We also want to identify a surrogate fluid that has similar properties and breakup mechanism as that of blood, so that can be used instead of blood to give us a lot of data from experiments. And also we want to identify a measurement technique that identifies sheet breakup, that identifies sheet thickness of blood, initial hole opening locations, and also measures the growth rate of those holes. So this is the experimental setup that I used to examine the sheet breakup process. We use a repeatable fast syringe injection coupled with a fan spray nozzle. It's used alongside with a high-speed imaging to capture the spray pattern before breakup. Another camera is also used for measurements of thickness of the fluid sheet. Some viscous and shear thinning fluids were tested for viscosity at different shear rates using a rheometer, and surface tension of the fluids were calculated using the pendant drop method. Now, explaining a little more about on shear thinning fluids, blood is a shear thinning fluid, which just means that its viscosity, unlike fluids like water, is not constant. If you increase the shear on the fluid, its viscosity decreases. Viscosity and surface tension tests helped us to identify a surrogate fluid within the shear rates tested, which showed similar shear thinning and surface tension behavior when compared to porcine blood. These are some of the image processing steps of finding the breakup length of fluid. We take the image, we normalize and binarize the spray image, identify a breakup threshold, and use that threshold to find the breakup length. The breakup threshold is simply the fluid to spray width ratio at which there is a sudden drop in the quantity of fluid. So we use that threshold to find the breakup length and then take an average of the mean images. The breakup length of all the fluids were tested, were computed, and as expected, the breakup length increases with increase in viscosity. The table below here shows a summary of the breakup lengths investigated. Similar to breakup length, these are some of the image processing steps for finding the initial hole locations. There are similar initial steps of normalization and binarization. Only the algorithm here identifies holes of a certain size and returns back its locations. This is a summary of the initial hole locations found in the different fluids. And as we can see, with increasing the viscosity, decreases the distance between the nozzle end to the initial hole locations. Of course, blood is an exception of that, as it is a shear thinning fluid and does not show typical behavior like viscous fluids. Now we summarize the result for the ratio between initial hole opening and the breakup length of the fluids. The idea was that this will help us identify a fluid which will show similar spray behavior to blood if we can match the ratios. But here we can see that even though our surrogate fluid had similar fluid properties to blood in its shear thinning nature and surface tension nature, it is still not a comparable match to that of blood. One reason might be the shear rates tested, shear rates experienced by the fluids in such spray events is higher than the shear rates we tested the fluids. Further experiments at higher shear rates are needed. Now we also want to look at the growth rate of holes in order to find its time scales, and this will have an impact on the droplet size later on after breakup. There is already a theoretical term that describes this behavior, and this is known as the Taylor-Kulig velocity, which is just the velocity at which the film of fluid retracts during hole opening, which is given by the equation shown here, which takes into account the surface tension, density, and thickness of the fluid. So from our experiments, we can plot graphs of the radius of the holes against time, and the slope of these plots will give us the Taylor-Kulig velocity. Experiment was repeated for 3 different velocities, and the track of 5 such individual holes in each of these sets were used to find the velocity. The line that we see in the graphs is an average of the slope of the 5 individual tracks of hole measurements, and so that is an average velocity experienced. The slope of that curve will give us slope of that line will give us an average velocity of the hole opening. Now we also want to measure the thickness of blood sheet at certain locations. For that we use the principle of beam deflection as it goes through a flat sheet. We can find the deflection of these laser beams as it goes through the sheet and then calculate the sheet thickness from the deflection measurements using this formula. So these are some of the results of the sheet thickness measurement, and as is expected, the velocity of the fluid increases the thickness of the sheet in the same location would decrease. So basically, the increasing the velocity basically decreases the thickness of the sheet, which is expected. These measurements are from 100 such images and are shown to be fairly consistent. Using the previous equation for Taylor-Kulig velocity, we can calculate the growth rate of holes from the thickness measurements. Ideally, for the Taylor-Kulig velocity to be applicable in our case, we would like the velocity from experimental images and the velocity derived from thickness measurement should be comparable. But as is shown in the plots right now, we cannot compare them. This difference is mainly because thickness measurements were done further upstream than where we start seeing holes forming. Holes in blood sheet are typically shown from our previous experiment to form around 4 centimeter downstream the nozzle end, but our measurements were done, our thickness measurements were done at 2 centimeter downstream the nozzle end. So we need to do further experiments in order to make the thickness measurements at or near the hole locations in order to correctly compare the velocities derived from thickness measurement to the velocities that we can find from experimental images. So in conclusion, we were able to implement a repeatable sheet breakup process as we see in crime scenes in lab using only a small volume quasi-steady fast stage. We were also able to get sheet breakup data consisting its intact length and initial hole formations. We were able to find a surrogate fluid with similar shear thinning behavior for the shear rates tested, but obviously higher shear rates needs to be tested to get a comparable fluid, as even though the viscoelasticity or surface tension fluids were surface tension properties were comparable, the spray pattern and the ratio between the initial hole location and breakup length were not comparable. We are also able to measure sheet thickness and Taylor-Killick velocity from our images, which will give us an idea of the time scale of hole openings. And knowing these time scales will be important in generating a predictive model for blood spatter, as they have a direct impact on the droplet sizes. With this, I would like to conclude my presentation, and thank you for listening to me. Questions, please.
All right, I think we're ready for a few questions for Labibia. All right, so let's start with our first question. So can you correlate the velocity of the droplets to the size of the blood stain seen in the crime scene?
Yeah, there's actually a very strong correlation in between the blood stains that we usually see in crime scenes and the droplets size or velocity that it's originating from, and there has been previously done many studies regarding that. Also, there has been studies where the blood stains are in like different materials, so wood, concrete, or other materials. So there are good equations that can relate the velocity and droplet sizes to the blood stains that you see, and from there you can back out the height from which the droplet originated from. So,
okay, understood. All right. So moving on to our next question: what is the variation expected in blood properties?
The variation in blood properties is not very high. Depends on the parameters that you are measuring. So if you're measuring blood properties, for example, viscosity measurements at different shear rates, then it would vary by a magnitude of 1 from low to high shear rates. But if all the other parameters are same constant, then the blood properties remain fairly constant.
Okay, thank you. Moving on to our next question. Why was the density matching not considered along with surface tension and viscosity?
So I did show surface tension and viscosity measurements. So density matching, I guess, was also considered, but I have not shown it because the density of blood is similar to that of water, and the surrogate fluid that we found, the one with water and xanthan gum and sodium chloride solution, its density was also actually quite similar to that of water and blood. So they are quite close to each other.
Okay, understood. So the expectation was that they were not going to differ very much.
Yeah.
Okay. So since you mentioned that, we'll talk about the complex. So it's a complex of different components. So should the optimal simulated fluid also be composed of a complex mixture of components or cells rather than a simple two-part solution? Are you adding extra things to your
Yeah, so that's a question I get a lot. So yeah, I mean, so our idea is to find a simple fluid that can be used to replicate blood. So if you have suspension like normally what blood is, but you would then always have to have that in suspension, and then you would have to go through an added step of making sure the liquid is properly suspended before you are trying to use it in your experiment. So ideally, we should be able to find a surrogate fluid that has the same properties as a blood minus the holes, keeping it in suspension part.
Okay. So I just have, I guess, a comment or a question. So now that you've done these experiments and you can, so you said translate some of that information to the height where the blood came from. So I imagine that would be quite useful in having that measurement, that quantitative number for an investigation. But what other kinds of things are you hoping to be able to translate this information into? We talk a lot about in the DNA community how about the presence of DNA does not indicate a particular activity. That doesn't, DNA could have gotten somewhere, through other kinds of means, like a secondary or a primary transfer. And so just the presence of DNA does not implement or indicate a particular, type of activity. Are there other kinds of things outside of direction or height that you're hoping to be able to model or to extract from the research that you're developing? I guess, how does this aid in forensic investigations? How would somebody use this to?
Yeah, so there's not much experimentation or data done on making good predictive models for blood spatters that you see. So this information, the fluid dynamics aspect of this information, which I am researching on, that we need to do in a much more efficient and better way to actually get the correct predictive models that we would see, because right now what we have is unfortunately it does not take into account all the fluid dynamics aspects of the blood, and blood is not a simple liquid, it's quite complex. So we need to study that, and there is viscoelasticity properties and how it breaks up, how it goes through primary and secondary atomization, and then we can correctly model what kind of splatters you would see. So that would just make the forensic analysis more accurate.
Okay. Yeah. No, I understand. So you're taking a very complex, multifactorial kind of situation, and you're looking at a small piece of it, and you need to continue to look at other piece of it before you're going to be able to create model. Okay, understood. But I really appreciate you taking the time to answer questions today. And with that, I'm going to encourage everybody to use sort of whatever minutes or whatever time that you have left here today to go and visit the poster session. We have over 30 posters, and I want to thank you so very much for joining us at the Forensic Technology Center of Excellence 2023 Graduate Research Symposium. Stay informed about more upcoming events by registering today with the FTCOE's weekly newsletter, and we hope everybody had a great day.
Before you leave today's webinar, I'd like to draw your attention to our feedback form. It takes less than 5 minutes to complete and can be accessed via the checkbox icon directly above the chat. Your honest feedback is invaluable as we continually search for ways to improve and provide the best experience possible. Lastly, across the top of the live stream window are links to our social media profiles, including Twitter, LinkedIn, and Facebook. There is also a link to the FTCOE website, the Just Science podcast, and the FTCOE newsletter registration. Like, follow, or subscribe to stay up to date with everything the FTCOE is doing in support of the forensic community. Thank you again for attending, and we hope everyone has a great day.